Hey folks, welcome to this episode on equilibrium concentration calculations, again using ice tables, but this case we're going to have a small KEQ and we're going to make a simplifying assumption. So recall that ICE or ice tables mean initial change equilibrium, initial concentrations or pressure. The changes, we denote that by X minus if it's a reactant plus if it's a product times the magnitude of its coefficients of the balanced equations. And then finally equilibrium concentrations. So these are just a summation of your I and C. Again, as stated in previous videos, if you wanted to use a rice table instead of ice table, the rice being the ratio of the balanced chemical equation, which then goes into our change, that's also acceptable. So in this case, this is our third type of equation. We looked at perfect squares, we looked at quadratic equations. Our type 3 is when we have a very small KEQ. Remember what a small KEQ means. It means that it's favored to the reactant. If we have a really small KEQ, remember times 10 to the negative 10 really means that the reaction didn't happen for all intents and purposes. So if we have something that's very similar to that, times 10 to the negative 9, times 10 to the negative 8, it means that the reaction has barely happened, meaning the change in the concentration will be very small. So if that change is very small, we can make things a little bit easier for ourselves, and we can assume that there has not been the change, or the change is so negligible that we can actually dismiss it completely. The way that we do that is we use this equation over here. We can look at one of the concentrations and divide it by the KEQ. And if that number that we get is going to be larger than 100, we can remove the change denoted by the X. So this is what we see. Again, we can look at a reactant concentration divided by our KEQ. If that is a huge number and bigger than 100, we can safely remove that minus X change. Now, if it's close to 100, you probably don't want to do this because the change is still pretty sizable. But if we're talking about like in the millions, the numbers a million or something like that, that means that the change is going to be small. Now, a note of this is that we're making the assumption that there's not going to be a change, or the change is so negligible that we can get rid of it. But there still will be a change. We just get rid of this for saving some time of calculation purposes. But there still is a change. If you really want to be precise, then don't make this assumption and just use it using the quadratic equation. So let's take a look at this example here. It says a chemist puts 0.085 mole of N2 and 0.038 mole of O2 in a 1.5 liter cylinder. If KEQ is 4.0 times 10 to the negative 8, what is the concentration of NO at equilibrium? Okay, so the first thing we know that we have to develop an ice table. This is an equilibrium. It's asking for equilibrium concentration, so we're going to have to use this ice table. Now, a few things that I noticed right away is that these are in moles. I'm going to need to get them into moles per liter. And the other thing is that KEQ is really small. So I'm going to make note that I'm going to have to see if I can use my rule of 100 here. So we'll do that in a couple steps. First thing, let's get these values into concentrations. So we use our C is equal to N over V. So in this case for N2, this is going to be 0.085 mole divided by 1.5 liter. And I get 0.057 mole per liter. Same thing let's do for O2. O2 I have 0.038 mole divided by 1.5 liter, and I get 0.025 mole per liter. Okay, so we have concentrations for our initials. Let's do our ice table here. So let's do one column for each of our species, and then we'll create I, C, and E. So I, C, E. This will be our concentration of N2, our concentration of O2, and our concentration of NO. Now, before we start, I'm just going to look at our balanced equation, make sure it is balanced, it looks like it. So I'm just going to put the ratios 1, 1, and 2. Okay? So again, those coefficients here act as those ratios. So my initial concentration for N2 is going to be 0.057 mole per liter, 0.025 mole per liter for oxygen, and 0 for NO. We don't really have anything produced before we start our reaction. Our change is negative for both of our reactants, and because the ratios are 1 and 1, they're both going to be minus x. For NO, it's being produced, so it's going to be plus, and our ratio is 2, so in this case, that's going to be plus 2x. Our equilibrium concentrations will be a summation of our initial and our change, so 0.057 minus x Here we have 0.025 minus x, and here we just have 2x. So we have our values. We're going to be using these values here to figure out what our equilibrium concentrations are going to be in addition to our K equilibrium expression. So let's do that now. So here are our values again, and our K equilibrium expression for this reaction is again products over reactants. So KEQ is going to be equal to our concentration of NO to the power of 2, because that's its coefficient, times concentration of N2 multiplied by the concentration of O2. So in this case, we can sub in our values here. Our value for KEQ is given to us right over there. So we get 4.2 times 10 to the negative 8, and that's equal to 2x bracket squared. Again, don't forget those brackets. That's a common mistake people make. Over 0.057 minus x times 0.025 minus x. Okay, so if we're going to make an assumption, this is the time to do it. We need to look at this K equilibrium value. We can choose either of these concentrations. I'm just going to choose this one over here, and we're going to do our rule of 100. So what that means is, again, we're going to take our concentration, and our concentration is going to be 0.057 divided by our K value, 4.2 times 10 to the negative 8. And what we get for this is we get 1357140. Now this number is very, very much larger than 100, so we can make this simplifying assumption. What this means again is that the change that we're going to experience here is going to be very, very, very small. Once again, because this K equilibrium expression, the value here is times 10 to the negative 8. The smaller this K equilibrium, it means that the more the reactants are favored at equilibrium. Now, if the reactants are favored at equilibrium, that really means, so if we remember that our KEQ is our concentration of our products over the concentration of our reactants. Okay? So to get this really, really small KEQ value, it means that this denominator has to be massive. And if that denominator is massive, it means that at equilibrium, we've basically converted almost none of the reactants into products. We're sitting over here. And so what that means is that the reaction almost didn't happen, and if that's the case, then our change from the initial concentrations is not that great. If we're still over here, after this reaction has happened, gone back and forth, it's almost like mimicking the initial conditions. So because of this, we can drop this minus x. Okay, so we can drop that, and that means our change is very, very small, which means that the initial concentrations and the equilibrium concentrations for these should be pretty much the same, because that change is going to be very, very, very small. So let's make this assumption and let's put this all together. So once again, our K equilibrium is going to be 2x squared, and because we've made the assumption that the change is going to be very, very small, we're going to have 0.057 times 0.025. So once again, we drop that minus x because the change is going to be so small, or we're assuming the change is going to be so small, that it's almost going to be like having the initial concentrations at equilibrium. So if we do this all out here, and we're going to also substitute our value for K equilibrium, which is 4.2 times 10 to the negative 8, and that's going to be equal to 4x squared, all over, if we put this in scientific notation, 1.425 times 10 to the negative 3. Okay, so if we bring this off to the other side, we get 4x squared is equal to 5.99 times 10 to the negative 11. To do this, we want x squared is equal to 5.99 times 10 to the negative 11 divided by 4. And also, we want to get it equal to x, so we can just square root the whole term while we're at it. So if we do all this, the value for x that we should get is equal to 3.86 times 10 to the negative 6 mole per liter. So that's our change that we're going to be expecting. Now you can see that the change is really, really, really small. It's a small, small, small number, times 10 to the negative 6. So if we had these values, which are 0.057, we're going to be subtracting this number from this, and you can see that that's going to be a really, really small change. So let's take a look at that. What would be our equilibrium concentrations? So for N2, what we'd have is 0.057 mole per liter minus 3.86 times 10 to the negative 6, and we get 0.0569. So if we round, we get 0.057. Well, look at that. That's the same. The equilibrium concentration is the same as our initial concentration. So that change is really, really small, almost so small that it doesn't make a difference. For O2, let's do the same thing, 0.025 minus 3.86 times 10 to the negative 6, and that's going to be equal to 0.0249. Again, rounding, we get 0.025. Again, look at that. Our concentration at equilibrium is the same concentration as our initial values. And again, these are mole per liter, mole per liter. Our concentration for NO is 2 times X, so 2 times 3.86 times 10 to the negative 6, and our value here is 7.7 times 10 to the negative 6 molar. So these are our concentrations at equilibrium here, here, and here. Now, to see if we made the right decision to remove the minus X change, we can plug our equilibrium concentrations into our K equilibrium expression and see if we get a value close to K equilibrium. If we do, that means, that the change is actually very, very small. If we don't, then we made the wrong decision and we have to go back and do the quadratic equation. So let's look at our K equilibrium expression. Again, it's the concentration of NO to the power of 2 divided the concentration of N2 multiplied by O2. Now our equilibrium concentrations that we got from before were 0.057, 0.025, and 7.7 times 10 to the negative 6. So we plug these values in, 7.7 times 10 to the negative 6 to the power of 2 over 0.057 multiplied by 0.025. And what we get, if we do this, we get 4.1 times 10 to the negative 8. So take a look at that. This is the value that we would have gotten if we omitted that small change. This is our actual K equilibrium value. So it is very, very close. We made a good decision in terms of getting rid of that. It makes our lives a lot easier. But once again, the question always arises, are we as accurate? No, we're not. We should have done the quadratic equation and accounted for that change. But when we round to two significant figures, it really doesn't make all that much difference. So that's it for this one, folks. We've gone through the 3 different types of scenarios that you would see: perfect squares, quadratic equations, and the one that we can make a simplifying assumption. So this does it for the equilibrium concentrations. Thanks for watching. We'll see you next.